My project is about bandwidth estimation-based TCP congestion control algorithms. There are several TCP variants, including TCP cubic and TCP Westwood. Cubic uses an cubic function to change the C-wing in order to improve the scalability. TCP Westwood is bandwidth estimation algorithm. In this project, we'll improve the bandwidth estimation function, and emulation have been tested. TCP Westwood is a TCP variant with sender-side bandwidth estimation and modification of congestion window. It exploits TCP packets to estimate bandwidth and continuously estimates the bandwidth by monitoring the ACK reception rate at sender side. The equation Bk is equal to the data divided by time inter-arrival time, and then the samples are passed through a discrete time low-pass filter. The congestion window equals to the bandwidth estimation times the minimum RTT. TCP Westwood Plus is the improved version of TCP Westwood. It differs from TCP Westwood that it works properly in presence of ACK compression. The bandwidth samples is equal to the data acknowledged during 1 RTT divided by RTT, and then the samples are passed through an exponential filter. However, both of them do not solve the C-wing limited case. The meaning of C-wing limited is that after sending out packets, the C-wing is exhausted and no more packets will be sent until an ACK returns at sender. Consequently, during that RTT, there will be an idle period. C-wing limited case will cause underestimation. As for the new bandwidth estimation algorithm, the timestamps will be checked, and from the timestamps we can subtract the idle period. The new equation is equal to the acknowledged data divided by Tk minus the idle period. Tk is the exact time when the sender calculates the bandwidth estimation for the case RTT, and Tr is the timestamp of the last received ACK during the RTT. Based on the bandwidth estimation function, two algorithms has been proposed. The first one updates soul-start threshold and C-wing using bandwidth times RTT mean when losses happen, while the second algorithm updates soul-start threshold and C-wing for every RTT, and when congestion is detected in order to make soul-start threshold and C-wing consistent with network capacity. The performance evaluation uses NS2 to do simulation and Emulab to do emulation. As for the results, the topology includes one flow figure and dumbbell topology. The parameter of the bottleneck, including bandwidth RTTQ limit, has been set up to simulate different network types. Here is the flow completion time results. The black columns are simulation results and the red columns are emulation results. 3 different types of networks have been tested, including WAN network, 3G and 4G network. The 3G and 4G network using trace data to simulate the varying bandwidth. The results show that the new algorithm, both of them can reduce the flow completion time, and the reduction is more significant in lossy networks. For example, when the loss rate is equal to 0.1% or 1%. As for TCP fairness, the fairness index function has been used. Fx is equal to the square of the sum of xi divided by n times the sum of the square of xi, where xi is the throughput of the ith connection and n is the number of connections. The fairness index ranges from 1 over n to 1, i.e. from the most unfair to perfectly fair. The results show that both Westwood M and Westwood N can achieve fairness. The conclusion is that the new algorithm can solve the C-wing limited case, and the sender keeps track both ACK reception rate and the time when each ACK is received. Based on the improved function, 2 algorithms have been developed, and both of them can reduce flow completion time. The results show that both of them can achieve TCP fairness.